Hello, I'm sorry I'm late. Oh my gosh. I looked at the clock and saw that it was 6:10 and I panicked. But here we are, picking up where we left off, doing fractions. Today we finally actually get to address fractions in any way, shape, or form. That is fraction basics. I have herein put in the dates for subsequent sections in the chapter 2, I should say. Review of fractions. Sketch this just a little bit that way. There we go. Now you can see everything. No, you can't. Yes, you can. Here we go. So today we are going over fraction basics. Tuesday we're going over simplifying fractions. The next Thursday, multiplying. Next Tuesday, applications of multiplication. And then that Thursday, dividing. And the subsequent Monday, we are going to do computer-related applications. Now, a little disclaimer going after this, I'm going to wrap up chapter 2, and I'm going to take a little break because I'm going to have a kiddo, and we kind of need the time and the space to take a nap. And I would hate to try to see what math looks like while, sleepy drunk. So we shall see. So today, going over the basics of fractions, we will describe the look of a fraction, the names, and why it's a part of a whole. So basically, we're going to get a fraction. Fractions tend to look like this: 3/5, 3/4, 1/8, 9/16, 2/15, and so on. Just anything where a number is being divided by another number. And we could take the time to show that 3 divided by 5 cannot fit into 3, so we put a 0 there. And we're going into decimal territory. So we drop, so 5 can fit into 36 times. So in decimal notation, a fraction like 3/5 would be 0.6. But in some cases, such as like 2/15, we have 2 divided by 15. 15 cannot fit into 2, but it can fit into 21 times. And there's a 5. 15 cannot fit into 5. We drop another 0. 15 can fit into 53 times, which would be 45. We drop a 5. And then you see how the cycle drops all over. Where these two will have a repeating number. In this case, it's 0 and 3. If it keeps on going forever and ever, we put a bar over the repeating numbers to show that it does, in fact, go on forever and ever. And because we have a repeating decimal, that's not a very neat notation. So that's why we have lovely fractions. Simply put, fractions, if need to be illustrated, and I will pick 3/4. So just assume we have this pizza pie, and that it's a perfect circle because this is a perfect math world. And we have cut it into 4 pieces. Now, a whole pie would be 4 over 4, which equals 1. 1 whole pie, because there's 1, 2, 3, 4 pieces of the entire pie. But 3/4, let's say we've eaten 3/4, we've eaten 3 of them. So now we have 1 remaining, but 3 of them are gone. So 3/4 of the pie. And going on, we have, and I'm going to try to draw this nice and neat. 1, 2, 3, 4, 5. Let's assume these are all equal. 3/5 would include 1, 2, 3 shaded out of the whole, which is 5. It is just showing how much of an entirety we're looking at. So we're looking at 3 pieces of the 5. We are looking at 3 pieces of the 4. We are looking at, and you don't have to do it with circles. Circles are hard. Rectangles are easy. You get this bar, and we're looking at 1/8. So 1 out of 8. 1, 2, 3, 4, 5, 6, 7, 8. Assuming they're all the same size, and it's 1/8. So that's pretty much what fractions do. This is what these numbers are talking about. Now, as far as the numbers go, we're going to look at this 3/5, a number in the top and the number in the bottom. The definition of what the top number is called is a numerator. And the bottom is a denominator. Because remember way back when we talked about denominant numbers, this one describes the pieces we're talking about, and this is a numerator, so it numbers off the pieces we're talking about. Let us see. So we have a quick example of a circle provided. I believe that's a halvesies, and another halvesies, and another halvesies. And 3 pieces are shaded in. Like pizza or cheesecake or cake or really anything that serves the purpose. I remember growing up we called it a pizza. To which we probably led to childhood obesity. We should probably have called this a salad bowl. So then we have 1, 2, 3 pieces that we're talking about for 1, 2, 3, 4, 5, 6, 7, 8. Another example is if we have a group of something, and we are talking about a section of them. So we count up the group, 1, 2, 3, 4, 5, 6, 7, and we're talking about 2 of the shaded in the 7. I don't know if you can hear my neighbors, but I think they're revving their engines for right now. All right, so we have another example, and this time just using words. We have a class. Well, words and numbers, so letters and alphanumeric characters. So a class of 23 has 15 girls in it. So that means 15, excuse me. That means 15 of the 23 are girls. So, now we have just talked about, in most cases, excuse me, let me get this situated. Nice and neat. Of fractions that have some number over a number. This is a proper fraction. Where we have a numerator and a denominator where the numerator is smaller than the denominator. An improper fraction is where the numerator is greater than or equal to the denominator. So instead of 5/9, if we had 9/9, or even like 17/9, where the numerator is bigger than the denominator. Now, an improper fraction, such as 17/9, we know when they are equal, 9/9 equals one entire thing. So if we have 9 pieces of that thing, and we're talking about all 9 pieces of that thing, we're talking about the whole thing. But in the case of 17/9, we are looking at, and we're looking at 17 divided by 9, because again, this is a division. 9 can fit into 17 one time. So minus 9, 17 minus 9 is 8. So there is a remainder of 8. And when we have a remainder of 8, we can rewrite this as 8 divided by 9, or 8/9. So this is a mixed fraction, or a mixed number, because we have both a whole number and a fraction. Sitting together, it doesn't mean they're multiplied, it just means that is the entire number. So what 17/9 looks like when you do a terrible job at pizzas. 2, 4, 5, 6, 7, 8, 9. Assuming these are equal. I know they're not, but this is why we assume, because not all things are drawn to scale. 1, 2, 3, 4, 5, 6, 7, 8. Oh, geez, I did it again. 9. So we're talking about 17 of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That's one whole pizza. 10, 11, 12, 13, 14, 15, 16, 17. And that's only 8 of this one out of 9. So together, that is 1 and 8/9. Okay, so we have an example to help reiterate with a list of fractions: 5/4, 10/11, 3/4, 8/5, 6/6, 13/10, 7/8, and 15/8. And notice, as in a fraction, when we have a number in the denominator and we're naming this fraction, the bottom has a th suffix. So if we were to write this out in words, especially 5/4, we have 5/4. So this helps us denote that, yes, it's 5/4, and it's fourths. That lets us know it's a fraction. So in this example, we are to circle the proper fractions and underline the improper fractions in this group. So proper fractions, again, are when the numerator is smaller than the denominator. So when it's smaller than the denominator, we will circle them. 5 is greater, 10 is smaller, 3 is smaller, 8 is greater, 6 is equal to and not less than, 13 is greater, 7 is less, and 15 is greater. So that means the remainder are improper fractions, and we will underline those. We have an example showing us an image of pies, like a pie chart. Where pieces of it are shaded. And we are to give the mixed number as to this shaded portion. So we have 1 whole, and 2 whole, and 3 whole. So 1, 2, 3 whole, and 1, 2, 3, 4, 5 pieces out of 6 of the remaining. And then to get to the improper fraction of this, you could sit here and count up all the pieces. So this would be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 6 and 6, 12. 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 23 over 6. Or you can multiply the number of holes by as many pieces that are in a hole. So 3 times 6 is 18, plus 5, which are already the pieces of the next part that is not an entirety, all over the 6. And then 18 plus 5 is 23. And this way is the faster way, but if you need to, you may still count up. So we'll have another example of that again. If we are given a mixed number of 5 and 2 ninths, to transfer that to an improper fraction, we have 5 times 9, which is 45, plus 2 all over that 9. So 45 plus 2 is 47 ninths. And to check our answer, we would simply divide 47 by 9. 9 can fit into 47 5 times. Minus 45, we get that remainder 2. So that is 5 and 2 ninths. So we can convert a mixed number to an improper fraction. So now we need to convert an improper fraction to a mixed number. We are given 48 sixths. So then we would simply take 48 divided by 6. And 6 can fit into 48 exactly 8 times with no remainder. So that means not only is this technically a mixed number of 8 and 0 sixths, because we have a remainder of 0, it is simply the whole number 8. Another example of this might be 42 fourths. Yeah, we'll go 42 fifths. This is a homemade example if you haven't noticed. So then we get 42 divided by 5. 5 can fit into 42 8 times with a remainder of 2. So that means 5 and 2 fifths. And to check our answer, we put it back into improper fractions. So 5 times 5 is 25. Oh, I'm so sorry. That's an 8. Aha! See, checking answers, very, very, very important. So 8 times 5 is 40, plus the 2 in the numerator is 42 fifths. So that works out, and that is correct. Oh. All right. All right, so we have a nice little word problem for an example. Martiza has 53 quarters in her bank. How many dollars does she have? So we have 53 quarters, and a quarter is 1/4 of a dollar, or 1/4. So we have 53 quarters. So we are simply transferring this from, we are taking this from an improper fraction to a mixed number. So that is 53 divided by 4. 4 can fit into 5 once. 4 can fit into 13 3 times, leaving a quarter left. So that means we have $13 and 1/4. And how we would write that out, especially in money form, would be $13 and 1/4 is 25 cents, because 25 times 4 8 be $1 whole. Oh, I think the neighbor baby crying. Bless her heart. Alrighty. And I think that's pretty much the basics of fractions going forward. We have some examples. I'm going to do every 4th example just because that seems the simplest way to go. Starting with the first, just because that seems nice and easy. So, number 1, identify the numerator and the denominator of each fraction. We're given 6/11. 6 is the numerator. 11 is the denominator. And then 5 asks, what fraction names the shaded part of each of the following figures? 5 being an object with 1, 2, 3, 4 pieces, 3 of which are shaded. Nine. We have if I can draw this right. Right, we have 1, 2, 3, 4, 5 pieces. And all 5 are shaded, which we know that to be 1. $13, we are given 8 pieces, which 4 or 5 of them are shaded. Ooh, 17 is a word problem, so bear with me. So this is asking a used car dealer sold 11 of the 17 cars in stock. So 17 cars in stock is what we are looking at. So that is going to be our denominator. What fraction names the portion sold? Well, if we sold 11, this fraction, 11/17, would be the answer to the first question of the fraction that names the portion sold. But what fraction names the portion not sold? So essentially, we're looking at the difference between a shaded region and an unshaded region. If 11 are shaded out of 17 pieces, that means 6 are not. So that means the fraction of not sold is 6/17. In problem 21, we are to identify each number in subsequent problems as a proper fraction, improper fraction, or a mixed number. 24, we are provided with 3/5. This is proper fraction. 25, we are given 6/6, which is an improper fraction. '29, we are given 4 5/7. This particular one, we have a whole number and a fraction. This is a mixed number. Okay. And now, number 33. In number 33, we are to give the mixed number that names the shaded portion of each diagram. So we have 1 whole and 3 parts of 4. So the mixed number is 1 3/4. Or you could say, you can find the improper fraction first and divide in by there to get your mixed number. It should also be 1, 2, 3, 4, 5, 6, 7 over 4. 7 divided by 4. You fit in there once with 3 remaining. So it'll be 1 3/4. All right. So get that nice and squared up. It'll think you're fine. Okay, you're good. Number 37. And subsequent problems, if you can see, okay, asks to convert a mixed or change to a mixed or whole number. So we are given 22/5. So 22 divided by 5, that's 4. We have the remainder of 2. That's 4 2/5. Number 41, we're given 59/5. 5 can fit into 5 once. Drop the 9. 5 can fit into 9 once. Minus 5 would be 4. Remainder 4. So the answer here would be 11 4/5. Sorry, 45, 46, so 41, 45. We are given 24/6. is 24 divided by 6, makes an even 4, with the remainder 0. So that is simply 4. Okay, and now for number 49, in subsequent problems, we are changing it to an improper fraction. So what we are given is 4 and 2/3. So we know we multiply 4 times 3 is 12, plus that numerator should be 2. Should be, oh, hello. Maple, come say hi. 14/3. Yeah. She likes fractions when it has to do with food. So we have 49, 53, which we are given 6 and 2/9, which 6 times 9 is 54, plus that numerator, which is 2, which is 56/9. 57. We're given 7 and 6/13, getting nice and complicated now. 7 times 13 is 70 plus 21, which is 91 plus 6 all over 13. So 97/13. And 61. We have 100 and 2/3. Well, 100 times 3 is 300, plus that numerator over 3. So 302 divided by 3, or 302/3. Right. So we have 65, which is a word problem, so one moment. All right, so we have 64 as a whole number and 0 quarters. So what we would do is 64 times 4. Oh, I'm sorry, it's the other way around. My mistake. We have 64 quarters. So 64 divided by 4. 4 fit into 6 once. 4 fits into 24 6 times. So that means $16. Oh, jeez. And the next one is a long word problem, so this will take just a moment. Get it to where you can read it while I write it. Oh, this is a research problem. One moment, please. All right, so this has a lot of research asking, so bear with me. I indeed will look this up because it said I can look it up on www.census.com. Get out my keyboard. Gov, that's important. All right. Data and Maps, Census Academy. Bear with me. So we are looking for the 2000 census. Oh, geez. The 2000 census, yes, please. So in 2000, we have, so that means the entire pie of the US in 2000. We were at 281,421,906 people as US resident population. So view by content availability. So A, we're looking for the population in Georgia as a fraction. So that means this lovely number is going to be our denominator. Georgia, how do I find that information? Interesting. Census data sets. Okay. This is going to be a lot of information, so give me a moment. This is a lot of research, my guys. have to get back with you on that one. Let's see. So let's see what I've got there. So, yep, a lot of research. 2000 census of Georgia. Pulling that up, taking its sweet time. May have to come back to this, because this is a research question more than a fraction question. I'll get back to you on this one on the next video, because this is going to take some time to research. And I will take screenshots and make it pretty and do like a whole thing, but I'll tack it on. It's very thoughtful. I would like to, if I may. I found the last problem to be kind of fun. I say, because you know me. I am a math nerd, and math is fun for me. Get a prop real fast. Because this has word in here which is not very decisive. All right. So let me write down the problem so you know what we're talking about. So this is problem 71, the last problem. Now I'm getting into the margins. Let's see. That should be. right, so what this says in essence. In statistics, we describe the probability of an event by dividing the number of ways the event can happen by the total number of possibilities. Using this definition, determine the probability of each of the following: obtaining a head on a single toss of a coin, or obtaining a prime number when a die is tossed. Now, a very simple thing, and if I can dig it out, I'll show you. Alright, so it's going to be a little loud. There we go. Is that in a coin, we have a heads and we have a tails. So there are two possibilities, and heads is exactly one of them. So A, that is 1/2, most definitely. There are only two sides of a coin, and to flip it, you'll only get one or the other. So the probability of getting a heads in flipping a coin once is 1 out of 2, or 1/2. Now, what's a bit it's a bit unnerving to me, but B, obtaining a prime number when a die is tossed. I assume that the book is talking about a D6, or a 6-sided die. So in a 6-sided die, if you roll a die, you can get a 6, you can get another 6, good grief. And that one's 4, and 2, and so on. So out of a 6-sided die, and we're looking for a prime number, 1 is neither prime nor composite, so it doesn't matter. 5 is prime. So 6-sided, there are 6 sides. 5 is prime, so we have 1, 2, 4, 5, 6. 1 is neither prime nor composite. 2 is prime. 3 is prime. 4 is not prime. 5 is prime. And 6 is not prime. So 1, 2, 3 sides out of 6 are prime. And that is assuming that we're working with a 6-sided dice. Now, what we do have, if you've ever heard of D&D, you know for a fact that there are more ways to roll a die. We have a 4-sided die. So the fraction thereof is going to have a 4. And we have, the point, which is 1, another point, which is 3, and 2, and 4. So we have 1, 2, 3, 4. 1 is neither prime nor composite. 4 is not prime, but 2 and 3 are. So that's 2 out of 4. So that's a D4, or a dice with 4 sides. 4, D5, D6, D7, D8. So a D8 is a dice with 8 sides to it. You can get a 1, you can get a 4, but it has 8 sides. So that means, dividing by 8, we have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4 are prime. So that's D8. The next thing we have is a D10. And you see, I'm nitpicking this problem because they were not precise enough with their question. This is kind of nitpickety, kind of rude, but it's in the textbook, so answer the best to your ability. So we're answering with every notion that I have. Now, granted, for D&D, for Dungeons and Dragons, there are D4s, D6s, D8s, a D10. What else we got? D12 and a D20, the almighty D20. We also have what's called a percent die, which is also just a D10, but it has 2 digits. So if you were to roll them together, you would simply say 38%, which also seems to be where my computer battery is at. I'll have to get back to you on that. So because they have the same number of sides, we're not going to consider the percent die just yet. So we've talked about D4, D6, D8. Now we're looking at a D10. Which has 10 sides. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4 out of 10. Next we have a 12-sided die. So out of 12, 1 is not prime, 2 is prime, 3 is prime, 4 is not prime, 5 is prime, 6 is not, 7 is, 8 is not, 9 is not, 10 is not, 11 is, 12 is not. So that is 5 12s. And then out of a D20, let us see if we can do any good. That is an 8. That's not too bad. The idea in most cases is trying to roll over a 10 or even a 15 if you can make it. But 8 is decent. It's not a natural 1, which is a critical failure. But what have you? We have a 20-sided die. With the denominator. So 1 is not prime, not prime. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17, 18, 19, and 20. So that should add up to be 20. So we have 5, 10, 15, 16, 17, 18, 19, 20. And these were prime, which would be 8 out of 20 on a 20 size would be prime. Okay, and now that I have nitpicked this problem, I will forego any questions, comments, and concerns. This has been a long enough day for all of us, I think, and I'm sorry I got started so late. Next Tuesday, the 18th? Yes, I believe so. Let me double check. All right, I'm just going to guess that it's the 18th.